Greetings everyone, I welcome you all to the presentation of the course CSE 221. The topic of the presentation is Biconnected components, and here I am Zunayedul Islam with my groupmate Sharmin, Akter, Keya will take you throughout the entire presentation. The topics we are going to cover here are description of the topic, formulation of the topic, pseudocode, simulation of the pseudocode, time complexity analysis, and use case. Description of biconnected components. In a nutshell, a biconnected component is a maximal biconnected subgraph in a graph. It sounds a bit confusing, but I'll take you through the entire concept so that you can understand easily. At first, let's know some overall overviews that biconnected component is a special property of two or more vertices in a graph, and if we fuse all those vertices or the components, it becomes an entire complete graph. Let's take for the example. Here we can see that 1, 2, 3, 4, 5, 6, these are 6 vertices. 1 is connected to 2, 1 is also connected to 3, but look carefully that 3 is not connected to 2. So 1 and 2 are mutually accessible. 1 can be visited by 2 and 2 can be visited by 1. So 1 and 2 are biconnected components. Then 1 and 3, the same way, they are also biconnected components. Now the formulation. What is the idea of biconnected components? To understand biconnected component fully, we need to know these 3 topics, and these are articulation point, biconnected graph, and biconnected components. What is articulation point? Articulation point is nothing but a vertex upon which deleting the graph is broken, which means that if a particular vertex in a graph, if we remove it, the graph becomes scattered or the number of connected components increases. Now, what is biconnected graph? Biconnected graph is such a graph where there is no articulation point. That means that there is no such vertex in the graph. If we remove the vertex, that the entire graph will not be scattered, or rather it will still be reachable from vertex to vertex. Now, the biconnected component. The biconnected component is a set of mutually accessible vertices from distinctive paths. And I said earlier that each biconnected component is also known as biconnected subgraphs, and that's why we had to know the idea of biconnected graph, and to understand biconnected graph, we had to know articulation point. Let's take a look at this example. Here, 1 to 12, there are 12 vertices and 14 edges, as we know from the formula, and there are 2 connected components. And which are them? These are 1, 11, 12, and 2, 1 to 10. These 2 are 2 connected components till now, and there are 3 articulation points. You see, articulation points are the vertices upon deleting which the graph becomes scattered. Now we'll see one by one that what happens if we remove them. Here, at first we have removed 3, and see the number of connected components have increased from 2 to 3. Here, this part, and this part has become independent and scattered. The graph is entirely scattered. In the same manner, if you remove 6, then the same thing happens. 1, 2, and 3 different connected components. And in the same way, if you remove 7, the same thing happens. So, what's the idea? If the articulation points are the vertices that tells us that how to look at how to distinguish the subgraphs. Here, if we see that if we subgraphify the entire graph, the graph will somehow look like this. That this is a subgraph, this is also a subgraph, another one, another one. And why such? Because these are actually biconnected components. Look carefully that this subgraph is mutually accessible. So for this subgraph, this one, and this one. And how did we find out? We shall go through this with the following slides. Stay with me. It's time for the pseudocode of biconnected components and how to find them. Before we jump into the pseudocode, let's see how to approach the pseudocode. The algorithm that we are going to use was invented by 2 geniuses, Hopcroft and Tarjan, long before even I was born. So jokes apart, there are 2 main functions that we are going to compile. I guess you have already figured that out. 1, finding the articulation points, and 2, printing the biconnected components. Let's have some idea that these 2 methods or functions both are recursive and both are based on linear DFS approach. Here, the first function that prints the biconnected components. Here, we have initialized some variables that we are going to use in the entire pseudocode. The first function, here it iterates over all the vertices, and upon iterating, it calls the function 2. We'll see what function 2 is later, but the function 2 always prints the biconnected components one by one. And here, as you have seen, that here is a disconnected graph, disconnected component. So for this part, this while loop is going to work, and it will print all the biconnected components of this particular component. Now let's jump into the most difficult function of the problem. Function 2. Upon it is called for each vertices, and it prints all the biconnected components according to the articulation points. Here we have initialized some variables and updated them from function 1. Here it traverses to all the neighborhood of the vertex. Here the v or the neighborhood, each neighborhood is made a child of u if it is not already visited, and then it is pushed in the stack. Then we call the DFS the recursive call, because there is not only one neighborhood, there are many neighbors in a vertex. There can be. So for this we call it recursive, and then we check that if the vertex is an articulation point or not. There are 2 conditions. These 2 conditions will be discussed later, and my partner will discuss later in the simulation. But let's see that there are 2 conditions, and these 2 conditions, upon fulfilling, the articulation points are denoted, and then we have printed all the edges of the articulation points so that they are biconnected components. Now here are another extra condition which prints the articulation points if it has no back edge. So it will also be described by my partner in the simulation. Now, a bit confused, right? Because I know that pseudocodes are not much understandable without simulation. So pseudocode without any input-based simulation doesn't make complete sense. It was said by the great Professor Anonymous Genius. Oops, that's me. So this as me, I am going to hand over my stage to my partner Sharmin at the piano.
Thank you, Zunayed, for giving me the stage. I'm Sharmin, Keya. I'm going to show you the simulation of the algorithm, time complexity, and the use cases. So at first, let's look at the simulation of the algorithm. Here we can see that we have a graph from which we need to find out the biconnected components. So according to the algorithm, we need to run DFS on this graph and find the spanning tree. We start from node 1, then keep visiting the adjacent nodes to find the spanning tree. So from 1, we go to 2, and then 3, and then 4, then 6. After that, we visit 7, and then after 7, we visit 8, then 9, and 10. But here we see there's no other non-visited nodes left. So we come back to node 6 and then we see that there's one non-visited node which is 5, then we visit 5. After completing the big connected component, we have another connected component left. So this is why we start from 11 and then visit node 12. Thus, we already visited all the nodes of the supergraph and also got the depth first spanning tree here. Now from this spanning tree, we have to find the discovery time for each node, also the low value of each node. Here, low value for a vertex means the lowest discovery time found after going through a back edge in the spanning tree. So the first node is 1, and the discovery time of 1 is also 1. Then we visit 2, so the discovery time for 2 is 2. After that, we go to node 3, and here the discovery time is 3. Following this, the discovery time of node 4 is also 4. After 4, we visited node 6. This is why the discovery time of 6 is 5. After 6, we visited node 7. This is why the discovery time of 7 is 6, and the discovery time of 8 is 7, and then 9 is 8, and the discovery time of 10 is 9. After that, we came back to node 6 and then visited node 5. This is why the discovery time of node 5 is 10. So then the left connected components discovery time is 11. Discovery time is 11, and 12 discovery time is 12. Now let's find the low values for each node. For node 1, we keep visiting the next node until we find a back edge. After visiting node 3, we found a back edge and we came back to node 1. We can see that the lowest discovery times from node 1, 2, and 3 is 1. So the low value for node 1 is 1. In the same way, if we start from node 2, then we find a back edge at node 3, we come back to node 1 through the back edge, and then we can see the lowest discovery value here is 1. So the node 2's low value is also 1. In the same way, we can find the low value of 3, which is also 1. In this way, we can also find the other vertices low value here. Now that we already found the discovery times and low values for all the nodes in our DFS spanning tree, we can use those values to create a DL table here. If we apply this formula to this graph, we will find out the articulation points. So if we look into the formula, we can see that if the lowest value of the child is greater or equal to the discovery time of parent, then the parent is an articulation point here. For node 1, we can see that for the child 2's lowest value is equal to node 1's discovery time. This is why this is true. And also for child 3, and the discovery time of 1 is also equal. This is why this is also true. But clearly, we can see that node 1 cannot be an articulation point because this formula isn't applicable for the root of this graph, and 1 is the root of this graph here. Also, if we look into the other node, which is 2, so here we can see that the lowest value of this node's child 1 is less than the discovery time of this node. This is why 2 is not an articulation point. We keep the found edges up until an articulation point in a stack. Here we can see that until now in the stack we have the edges 1, 2, 1, 3, and 2, 3. Also for node 3, we can see that node 3's child is 4, and the lowest value of 4 is 3, which is equal to the discovery time of node 3. This is why node 3, this formula is true for node 3, and thus we can find out first our one articulation point here, which is 3. Since we found an articulation point, we can pop the elements of the stack, and those will form one of the biconnected components here. After 3, we can see in the node 4 that node 4 is also false if we put it into the formula, and also node 5 goes as well. Until now, in the stack, we have 3, 4 edge, 3, 5, 3, 6, 3, 4, 6, and 5, 6 edges. Then we found another articulation point here, which is node 6. We can see here that formula is true for node 6. Since we found another articulation point, we can pop the elements of the stack here also. This is how we got another biconnected component here. After 6, we can see node 7 is also an articulation point because the formula is true for node 7 also. Thus, we already had node edge 6 and 7 in our stack, and we already got an articulation point again. So we will pop out the edges from stack here, and we also got another biconnected component here. For node 8 and 9, we can clearly see that these two are false for the formula, and then now there's no more unvisited nodes from this connected component. We can pop rest of the edges in the stack. The edges right now in the stack are 7, 8, 8, 9, 9, 10, and 10, 7. These will form another biconnected component. And since there's another connected component in our supergraph, so we will also look into the node 11 and 12. Node 11 is true for the formula, but node 11 cannot be an articulation point because node 11 and 12 are different from the first connected component. But 11 is the root node here. As there are only 2 vertices in the stack, there's only one edge, and it will create another biconnected component here. We can visualize this by these graphs, that this is our supergraph, and from this supergraph we got these subgraphs, and if we subtract these subgraphs here, we will get this biconnected component, this one here, and there's another one, and there's another one. We will get fully 5 biconnected components here. And the edges we popped out from the stack are here. The first biconnected component is this one, and the edges we got from here is 1, 2, 1, 3, 2, 3. And the second one is here. We got the edges from this biconnected component is 3, 4, 3, 5, 3, 6, 4, 6, and 5, 6. And after that we got this biconnected component here, and the edge from here we got is 6, 7. And after 6, 7 we got this biconnected component, and here we got these edges which are 7, 8, 8, 9, 9, 10, and 10, 7. And lastly we got 11, 12, which is another biconnected component. So after all this, we got our output, which is we got 5 biconnected components from our supergraph. Now the time complexity of this biconnected component algorithm here is bigger of b plus e, because function 1 we can see that function 2 is being called for all vertices in the graph. Function 2 is nothing but a recursive DFS algorithm, and we all know that DFS algorithm's time complexity is big of b plus e, where b represents the vertices of the graph and e represents the edges of the graph. This is why the time complexity of finding biconnected components here is bigger of b plus e. Now, if we look into the use cases of Biconnected components, we can see there are many use cases of Biconnected components in our world, but these are few we will describe here. First, roads. In this case of road, Biconnected component algorithm helps us determine roads which can be easily traveled from one to another, and also helps us find out roads which, if blocked, there will be so many disruption that transportation will be hampered, or people cannot go from one place to another place, since the failure of an particular point or road in this case will prevent access to another roads. This is why this algorithm is really effective for roads. And also we can see in computer networks, to verify the strength of the network, we use Biconnected components here. We can find out the components in the network which can function even when a node fails. So we can find the articulation points and remove those articulation points to avoid such problems. Because in computer networks, we all know that an articulation point means if the computer in that network fails, then the whole computer network will fail. In communication network, we can see that in real life, our communication network can also be analyzed with Biconnected components. We can find out the group of people who can keep functioning together even when someone in the group is absent. Also, we can find if there is any person in a network without whom the communication falls out. In every group, we know that there's few people without whom the communication of that group cannot be a real success. So these are all from us. Thank you so much, and stay well, stay safe.